Okay, this is AS Statistics. We're on Chapter 1 and we're looking at grouping data, class, boundaries and width. First of all, a very straightforward thing. So group frequency tables are used when the data is widely spread. Consider the following data on spectators and football matches, discrete data, and construct a group frequency table. I'm not going to go through this whole question video. My videos are boring enough. But obviously we're looking here, then that goes from 0 to 9999. So our next group then would be 10,000 to 19,999, and then we would have 20,000 to 29,999, 30 to 39,999, and then 40 to 49,999. And the way you're supposed to do this, whether you do it like this or not, is you look at the first one. If you look through and try and count all the ones between 10,000 and 19,000, you're going to make a mistake, I guarantee it. So you look at the first one and you go 2, 3, 4, 5, 6, and that's one for there. 4, mark them off then as you go. 2, 8, and you work your way through. I'm going to let you work away at that. I'm going to pause the video, and you should end up with 1, 21, 12, 4, and 2, and they should all then add up to 40. So that's obviously just discrete data, they're in whole numbers as people at a football match. So we have that. When you're deciding how to group, you need to be careful of the size. If the number of classes is too large for the amount of data you have, then the frequencies will be too small to build up an idea of the shape of the distribution. What we're saying there is if you do kind of 0 to 25 and 25 to 50, then you're only going to have two groups and you don't really kind of see how the data is spread out. On the other hand, if there are too few classes, becoming too crude would kind of lose detail. Sorry, as in if you've too many, as in, sorry, I've got that the wrong way around. If you kind of, each 1,000, you're going to then have 50 different groups working your way down. Or if you have too few groups, then it's kind of hard to see the shape. So the best choice of class intervals gives enough detail to get a feel then for the distribution. Here we have it then for continuous data, and again I hope you can see what way this has to work. So it's going to then be 1.7 less than or equal to h, less than or equal to 1.75, 1.75 up to 1.8, 1.8 up to 1.85, 1.85 to 1.9, 1.9, 1.95, and you can see then there's no gaps in that data, obviously, whereas up here, there's no number in between 19,999 and 20,000 because you can't for spectators. That's a discrete and continuous difference there, obviously. Again, I'm not going to go through this one, but the way you would do it, you go 1.85. 1.85 obviously needs to be in this group here, not this group here. It's a good example to start with. 1.78. So I think it's going to be in that group. 1.65 is going to be in that group, and so on. And again, if you work your way through there, you should get 5, 5, 3, 3, 3, 1, and there are 20 pieces of data. So that then comes to 20. Okay, on to taking a closer look then at some of the classes and looking at class boundaries, class widths and midpoints and stuff like that. So our lower class boundary in this one is reasonably straightforward, 1.65. That's a cutoff point for that group, and then the cutoff point for at the top end is going to be 1.7 or 1.70. The class width then, and you might want to write this down, then is going to be the difference between the boundaries. Now be careful, they're not always as obvious kind of as these ones here. And so let's take away this, so that's going to be 0.05, and then our midpoint is then the average of our class limits. And this case is going to be 1.675. It's obviously the halfway point between our 1.65 and our 1.7. If the intervals have been expressed as 5 to 9, 10 to 14, it is clear that the original lengths have been rounded to near a centimetre. In these cases, you need to consider the upper and lower bounds of each interval. So if it's 5 to 9, and the previous group then is maybe kind of 0 to 4 or something like that, you need to kind of take into account maybe something that was 4.8. So the lower class boundary here is going to be 4.5. The top end then is going to be 9.5. Our class width then, the sum was 9.5, take away 4.5, and in this case that obviously then gives us 5. So just be careful there, it's not as obvious as the previous one. You can't just do 9 take away 5, that's going to give you the wrong answer. And then our midpoint is 9.5 plus 4.5 divided by 2, and that gives us 7. Alright. Next example is a good one as well. Age is very different than the other things. So if it's classes between 13 and 16, they can't have been 12 and a half. If someone's 12 and a half, you don't call them 13. Age is kind of classified differently than most other kind of groups. So the lower class boundary here is 13. If you're 16, you're 16 all the way up until the day you're 17. So our upper class boundary then is going to be 17. Our class width, 17 take away 13, is going to be 4. And then our midpoint, 17 plus 13 over 2, gives us 15. Be careful when a 0 is included, that messes stuff up as well. So you have 0 to 5 and then 6 to 10 or something like that. The 0 kind of plays havoc with this a wee bit. So if it's the nearest centimetre, the lower class boundary is not going to be any smaller than 0. However, at this end, it's going to go up to 5.5 if it's been rounded to the nearest centimetre. The class width then, that's an easy one, 5.5 take away 0. That gives us 5.5. And then our midpoint is 5.5 plus 0 divided by 2. So our midpoint in this case is 2.75. I always find that quite frustrating, because then for the next group up, if it goes in from 6 to 10, the midpoint don't really kind of marry up with the other groups because of the zeros will sort of mess it up. Our class in 10 to 14. So the data is discrete here. So 10 to 14 pupils, the lower class boundary is going to be 10. You can't have 9.5 pupils, doesn't make any sense to. Upper class boundary is going to be 14. Class width is of course 14. Take away 10. That gives us 4. And then our midpoint, 14 plus 10 over 2. And that then gives us 12.